Hi, so my name is Bill Buchanan, and I lead a podcast series on the world leaders in cryptography. And today I have a true world leader in Daniele Micciancio. Hi, Daniele.
Hi, Bill. Thank you for inviting me.
Thank you. Daniele is a professor in the Computer Science and Engineering Department at the University of California, San Diego, and was elected as a prestigious IACR Fellow in 2019. His main focus is on the foundations of lattice-based cryptography and the advancement of applications based on it, including fully homomorphic encryption. Daniele has published many classic papers related to lattice-based methods, including working with Chris Peikert on trapdoors for lattices and Oded Regev on the worst case to average case reduction based on Gaussian methods. He has also contributed greatly to the advancement of bootstrapping methods, including defining the DM FHEW method along with Leo Ducas. In 2002, he published a classic book on the complexity of lattice problems, a cryptographic perspective with Shafi Goldwasser. And in 2002, he published a paper on generalized compact knapsacks, cyclic lattices, and efficient one-way functions, which was given the FOCS 20 Years of Time Test of Time Award. This paper led to the theoretical foundations of efficient lattice-based cryptography. His paper with Regev also received the FOCS Test of Time Award in 2024. Quite an achievement overall. So what's your current role and what does a typical day involve for you?
Well, I work at University of California, San Diego, so I'm an academic. As most academics, the work involves many different and competing things, each one of them claiming to be the most important. But my work is split between, of course, teaching and educational activity, both at the undergraduate and graduate level, and so teaching classes. Research, of course, is a big part of it, and there is also quite a bit of administration, something that typically as a student you don't get to see, but yeah, once it becomes a real job being at the university. Part of you is still a student, you still live in the university environment. That's something that I really like. I think it keeps you young inside, at least. And yes, the typical work is the typical day is every day is different. One of the nice things about academic jobs is nice. I'm not sure. Maybe it's not also as positive. Is that there is not a fixed schedule. It can be very bursty, and sometimes you have to prioritize one thing over something else. For example, during the academic year, it is hard to find as much time for research. Often, a lot of research gets done during the summer, where we enjoy a pretty long summer break. It's a break from teaching. It's when most of the research gets done. On the other hand, during the year, research is done part in collaborations with other scientists all over the world. Part of it is just by yourself. Part of it is with grad students. And research with grad students, or also undergraduate students, is a mix between research and education. There's a component to it which is training the students, especially in their early years when they get started. And then they progress through their doctoral program to become essentially peers, your collaborators, which are at the same level as you are. And on the administrative side, there's really a lot at all levels, department level, campus level, outside of the university. There's a lot of work involved in evaluating other people's work. Peer review is a very important part of the academic reviewing, of the academic publishing process. And reviewing can also be helping government agencies to fund research, helping them evaluate the proposals that get submitted. And of course, I have to write also my own research proposals to get my research group funded. And typical day is okay. So I tried to research. If I just have 1 hour or 2 hours, I don't even try to do it. It requires focus. So usually I try to set some time where I can focus on research. Certainly not every day, and then the other activities can more easily broken into pieces, and you prioritize depending on deadlines. It's a deadline driven work. And another research, I like to take it as a long term activity. I never worried about submission deadlines. You work on the problem, you try to solve the problem. When it is ready for submission, for publication, then I send it. Everything else is often done under the pressure of some impending deadline.
That's good. And so, what were your school days like? What were you like as a school pupil?
Oh, school. You mean like elementary school? Okay, or
Your
middle, high
whole of
school?
your
Yes. Yeah.
education, what were you like? How did you progress through from school to university?
Yeah, I mean, it's not as a pupil, it's not that you're given the choice. I mean, you have to go to school. But I didn't mind. I wouldn't say that I loved going to school. Very few pupils do, and it's something. Part of it is also uh, is. Social pressure. I mean, if nobody seems to like to go to school, then yeah, you shouldn't do. But I did like. I remember I liked mathematics since early on, and that was my favorite subject. And mathematics was not just the mathematics that you study at school. In fact, primarily was the mathematics that you could get exposed to outside of it, like solving puzzle type of games.
Yeah,
There is this game component of mathematics that make it really, really attractive to me.
yeah, yeah. In cybersecurity, we often get our students to solve cipher puzzles, traditional ciphers like Pig Pen and Caesar ciphers and so on. I think it's good exercise for the brain. So, what got you into cryptography?
Yeah, the cryptanalysis and cipher thing is great. Unfortunately, that's not something I ever got exposed to through school
Mm,
or even through college, university.
mm,
Cryptography is something I learned about much, much later, only in grad school. I learned about cryptography, and I also started appreciating. I knew the word cryptography. I knew there was something called cryptography, but I knew so little about it that I simply couldn't even appreciate it. So during my school days, yeah, I was gravitating more toward mathematics and computer science at large. So the computers I remember was something that I liked since early on. My first exposure to a computer-like device, I think, was already in elementary school. And it was not even a computer, it was just a calculator, but it was one of these Texas Instrument
mm,
programmable calculators where you
yeah,
could write little programs. Programs were written in something that looked more like
basic.
assembly. I mean, these
Yeah.
three-letter instructions. I forgot the model, TI something. Yeah.
Oh, yeah, yeah.
And it only had this small red liquid crystal display. And so it could only show numbers. That's the only thing you could do. But the fact that you could give instructions,
Mm,
get the
mm,
thing to do what you want, and then do it on its own, is something that I found fascinating. I mean,
mm,
that's something that doesn't, you cannot do with people. You tell them to do
no.
something, they will typically do whatever they want. But yeah,
Mm,
with computers, yeah, so you can play with them and they will respond in a predictable way. And then from there, I moved into home computers. This was in the early 80s.
mm.
So it was the time when home computers became popular. Remember
Commodore, Spectrum.
Spectrum, yes.
Yeah,
Yeah, yeah. ZX Spectrum.
yeah,
16 kilobytes of memory, which at the
yeah.
time seemed like a pretty
It
good
was a
amount of
lot.
memory. Oh, you can do so many things. Because
Yeah,
there was a 64 kilobytes memory expansion, I
yeah,
think, or
yeah,
48,
yeah,
but it was too expensive, so I don't
yeah.
think I ever got it.
And it kept falling off too. You needed to put some blue tack onto it.
So cryptography is something that I discovered only in uh, um, at MIT during my doctoral studies. I was a PhD student there. I went there by chance. I think it's fair to say that was not exactly a targeted choice. And I went there without really knowing what I wanted to do. I went there because somebody suggested. This is a professor that I met in Italy when I was a student, Senjoy Mitter,
Hmm.
who was a professor at MIT, and
Yeah.
he also had a position in Pisa, the university where I was studying in Italy. And he told me, Daniele, I think you should apply to MIT. And I applied to MIT just to follow his advice.
Mm.
It was a
Yeah.
great
Oh,
advice. It was a very, so it was a, yeah, so going there was great. But it took me some time to figure out what I wanted to do. So during the first year, I was kind of lost. During the second year, I started taking cryptography courses with Shafi Goldwasser,
yeah.
in
Hmm.
part because there was a very strong cryptography group there. I mean, there is still a strong cryptography group. Shafi
Hmm.
Goldwasser, Ron
Run
Rivest,
Vest,
Silvio
additional.
Micali.
Yeah. Yeah.
And at the time when I was there was particularly active. They also had Adi Shamir visiting on
Yeah.
sabbatical for 1 year and Oded Goldrake also
Wow.
there
Wow.
for 2 years. So
Yeah.
was
Lenny Doman too.
no, Lenadam was not there at the
No.
time.
Yeah. Yeah.
So that there was so much activity, and then of course professors they had students. Was a very active group, and after taking one or two courses, I decided perhaps that's something that I could do for research. I talked to Shafi, and that's how I got into cryptography.
Yeah. It's amazing. And you've researched and taught so many different areas. What's your favorite area of cryptography?
I think everybody expect me to say lattice-based cryptography, and that's the area that I dedicated most of my career to. So let me mention something else, an area that
Mm.
I like, and I think is very interesting is the formal analysis of cryptographic protocols and the intersection between cryptography and formal verification and logics of security is something that so the fact that I've never been a full time cryptographer. My interest in computer science were broader. Yeah, they got me to look often into other areas. Area of interest, a secondary area of interest of mine is programming languages. Not that I do
Hmm.
any research in programming languages. That's what I
No.
was doing in Pisa when I was an undergraduate student. I had looked a little bit into research. That's all I knew, and since then I kept following a little bit what's going on without being active as a researcher in the area. And I see some very interesting opportunities to be explored between crypto and languages. But we can get back to, I expect I have more interesting to say about lattices, so we can get back to this later on, perhaps.
Yeah. That's right. And so could you just outline how lattice cryptography actually works? I know it's really difficult,
Oh,
and I
it's
don't think
not.
I've ever seen anyone in the world that's really given an easy answer. So perhaps you, as a world leader, could inform us.
Yeah, yeah. So first of all, I like to make things simple. Whenever something is hard to understand, I'm not satisfied about it. So I spend actually quite big amount of time in trying to find things, try to find ways to describe things in a simpler way. That's something that I do not only to communicate to other people. It's something that I find satisfactory for myself. And if something is hard to explain, I think that oh, that means I still don't understand it well enough. So lattice cryptography, if yes, different people, of course, every person will give you a different story, different perspective. They're all interesting, and the fact that you can look at it from different perspective, perhaps is the best way to understand it. So let me give you the perspective that I like best is forget about lattices. Don't worry about lattices at first. Just think about one of the most basic problems in computer science, the subset sum or knapsack problem. You are given a bunch of numbers, and then you are given a subset, a random subset of those numbers. and you add them up. You are not given the subset. You're only given the sum. And the question is, can you find the subset that adds to it? And this is one of the classic NP-hard problems already mentioned, analyzed by Dick Karp back in the early 70s. And the problem is very simple to describe, just integers, very familiar mathematical objects. Now, how you go from here to lattices? So this problem already captures the nature of lattice cryptography. You have a secret subset, you only give the sum, from the sum it is harder to recover what the original set was. So you can embed these numbers in a high-dimensional space. Just add extra coordinates and put a little number, epsilon, on these extra coordinates so that these numbers become vectors. And they are linearly independent because they have this extra coordinate. And the coordinate is very, very small, so it doesn't really matter. It is still a subset sum problem. But once you embed the problem in high dimension, when you take combinations of the numbers, you're also combining these extra coordinates. And you can change the set of vectors in n-dimensional space in a way that turns subset sum into a geometric problem. So you have now you have points in n-dimensional space, and the fact that you are in n dimensions allows to embed trapdoors into the subset sum problem. So you can represent, you can give many different bases for the same lattice. Just like as in vector space. And you can have a good basis, you can have bad basis. And the good basis is a basis that allows to solve the subset sum problem using the extra coordinate, using geometric methods. But you can give out a public basis for the same lattice that doesn't reveal what this trapdoor is. And using that, subset sum is a notoriously hard problem. And not only in the worst case subset sum, there is strong theoretical evidence that it's hard to solve on the average, which is what is needed in cryptography. You want to know that when you pick your key, cryptographic key at random, you want to know that your key is hard to break with high probability. It's not enough that some other worst case key is hard to break. The adversary cannot break every single key. You want your key to be hard, at least with some degree of confidence.
Yeah, that was an excellent explanation. So I think one of the applications of your work is in fully homomorphic encryption. And what you do is you have a key pair, public key will encrypt data at its source, and then we can then process the data, and then at the output, we can then decrypt with the associated private key. So could you explain the main generations of fully homomorphic encryption? I think it's went through various iterations and there's been various advances. Some people say there's 3 or 4 generations that it's been through. Could you just explain those generations?
Yeah. So before the generation, let me address what is the connection between fully homomorphic encryption and lattices.
Yeah.
Or homomorphic encryption, generally speaking. So lattices we see something similar to subset sum. You're adding up numbers. So you have an algebraic structure. You can perform addition of lattice vectors. So this is something that translates in a pretty much direct way into encryption schemes that are linearly homomorphic. You compute the addition of ciphertexts, and when you add up ciphertext, you're also adding up the corresponding messages. And this is very, very efficient. Of course, this is not the first encryption scheme supporting just one operation. Fully homomorphic encryption allows to perform arbitrary operations, and that's the real breakthrough. So generations. I'm not particularly fond of this classification into generations, and you will find it's more of a branding thing, and you will find different people classifying things differently. And but there is something to it. I mean, trying to do it is good. It's fine. I mean, no objection to that. It's a way to try to systematize and try to understand how different systems relate to each other. There's been so much work in the area that it can be overwhelming to look at those schemes and classifying them into generation give some kind of framework to do that. But I think that the schemes, in the end, so they are all lattice-based, and they actually share much more in common they have much more in common with each other than what some of these classifications may suggest. And also is never clear. So there are many small differences, but then which one is the one that should be used to draw a line between one generation and another one? It depends on your perspective. Often it is done along the lines of software libraries and implementations, but that shouldn't really be the main issue. There is mathematics underneath it. So, okay, so generation. So you asked for to do that, so I'll do it, okay? So I will start with something that I call generation zero. Okay, I don't start with one, I start with zero, and that's the Craig Gentry first proposal. So that's a breakthrough paper in 2009 that for the first time showed, in a sense, that you can do fully homomorphic encryption. Now, the way we do fully homomorphic encryption today is very different. In fact, most other generations, they use lattices in a very different way from the way it was used in Gentry's original proposal. And that's why I call it zero. But so that paper made a really fundamental contribution, which I think is underappreciated. So we typically focus on the technical contribution, on the math and the hard to understand things. I still think that the main contribution of the paper was to convince the community that the problem was solvable. It was not the solution itself, but really, that was the turning point. Before then, cryptographers, you could divide them into two camps. Those that thought that fully homomorphic encryption was a nice, interesting open problem yet to be solved. And those thinking that it is just impossible. The open problem is to prove the impossibility. There is something contradictory about encrypting and being able to perform arbitrary computations on it. So Craig's paper really changed. I don't know if there were still people trying to prove impossibility. And at the time, but I think that the vast majority of the community, at least after seeing his paper, decided that yes, this problem can be solved. Perhaps this is not the best solution. Perhaps it's not the right solution. Perhaps it's not a solution at all. It was based on some novel way, or at least a less standard way to use lattices, which perhaps will get broken. Who knows? We already had better ways to do standard public key encryption using lattices than with better theoretical foundation than the way it was used in his proposal. But once he did that, so this is something that really put lattices under the spotlight. So the implication is something that I think goes way beyond FHE. So the rate was not the only one. There was also a lot of work especially by Chris Peikert and others, in greatly expanding the class of applications that can be solved using lattices. But FHE was something that could be solved only using lattices, was the only way. So many more people started looking at lattices seriously as the only option to do that. So progress was quite fast. So shortly after a couple of years, in 2011, I believe, Brakersky and Vakuntanathan came with a method to do homomorphic encryption, still following Gentry's blueprint of using this bootstrapping technique, which is the main conceptual contribution of Gentry's work. So still using that, and that technique is still used today, it's still used everywhere. It's the only method that we know how to build a fully homomorphic encryption scheme, with a few exceptions. But they were able to base it for the most part on what we consider to be standard lattice-based cryptography. And different people may have different opinion about what is standard and what is not. But so what I like to consider standard is something for which there is a theoretical foundation and a solid theoretical foundation. And lattice cryptography is something that started in the mid-90s with a paper of Miki Aitai. That's the paper that showed for the first time that there was a connection between the average case and worst case complexity of lattice problems. And it could only build one-way functions. So in terms of applications, it was not particularly attractive. It was also terribly inefficient, the one-way function that you would get out of it. But still, it was pointing a specific way to pick lattices at random and at certain lattice problems for which we could say with confidence, yes, we expect these problems to be hard on average, the way you need for cryptography. And even variants of this problem, so this is called the short integer solution problem, SIS. And even variants of these problems, including the learning with error problem, LWE problem introduced by Oded Regev in 2004, 2005, is something that is still using exactly the same distribution on lattices. It's a variant of the SIS problem with an injective function rather than a surjective function, but still based on this average case connection. Oded, in order to prove that his problem was hard, he had to go through a different technical result. So the average case worst case connection is different, it uses quantum computation, but still it was exactly the same lattice distribution. So the DV Brackersy-Vakunthanatan system was building fully homomorphic encryption out of this basic machinery, and that's the first generation, what I call the first generation.
This is integers.
Yeah. So then when it comes to subsequent generations, then that's when things start diverging. You will find different pictures and different stories. A paper that is certainly a fundamental milestone in the development of fully homomorphic encryption is the GSW crypto system of Gentry, Sahai, and Waters, which originally it was described as a completely new method to do lattice cryptography. The idea was, the message is an approximate eigenvalue of a matrix. So when you add or multiply matrices, you get the sum or the product of the eigenvalues. These are eigenvalues with the same set of eigenvectors. The eigenvectors have to be kept secret. That's the secret decryption key. And how do you decrypt? You multiply and you see by how much the eigenvector gets multiplied. But you need to keep the matrix secret. In order to keep it secret, you cannot, in order to keep the eigenvalue and eigenvector secrets, you need to keep, you cannot reveal them. So you use approximate eigenvectors rather than actual eigenvectors. Now, this had some far-reaching consequences in building identity-based fully homomorphic encryption. But in retrospect, it turned out that what they were doing was not as new, technically novel and different from what we already knew how to do it. One of the main building blocks of the Brackersy-Vakunthanatan crypto system was a method to switch between keys. You have a message encrypted under key A, and you want to turn it into a ciphertext encrypted under a different key, B. So, I mean, normally you cannot do that. If somebody sends a message to you, Bill, if I can change it into a ciphertext encrypted under my key, then I can decrypt it. Yeah. So in order to do this, you need some key material. So you can release a key material, which is, in your case, would be an encryption of your secret key, B, encrypted under key A. And this can be used to translate messages from one key to another. Now, this was the cornerstone of the first generation encryption schemes. And the way they were doing addition and multiplication of ciphertext was completely different. So this key switching was used for efficiency purposes, to switch, to alternate between large keys and small keys and allow to perform what you want while managing the complexity. Now, decryption in lattice-based cryptography, and this is the key feature that allows to do all these interesting things, is for the most part, the decryption operation is linear. So we've seen how subset sum is a linear operation. Decryption also is, for the most part, a linear operation. It's a linear function followed by some rounding to remove the errors. And this decryption operation can be done homomorphically. So the switching key is so you have your key, encrypted under A. Since lattice encryption is linearly homomorphic, you can perform this decryption homomorphically, and you get the message encrypted under A instead of B. Now, if instead of giving you an encryption of your key, of B, I give an encryption of a multiple of your key, when you perform exactly this same key switching operation, you will at the same time decrypt and multiply your message. So you perform a decrypt and multiply. And this is, if you write down the program, if you implement it, if you look at the input and the output, this is exactly the same as the GSW encryption scheme. It's a totally different way to do it. It took me quite a while to finally understand that's really what was going on. And I mean, the GSW was clearly a very, very interesting crypto system, but it seemed to be, the fact that it was isolated and different from everything else is something that turned out that, oh, that's because it was hiding something. Not that the authors were trying to hide it. It was not clear to them. They were genuinely thinking that it is a completely different way to do encryption. But it was just key switching, but using this, something you may call a functional switching key. It's a switching key that as you switch, you're also applying a function to the message, which in this case is just a multiplication by some constant. Now, since the switching key is itself a ciphertext, it is encrypted, so this constant C is also encrypted. So you can think of the switching key as an encryption of C. And once you do that, you don't even need to switch keys. Think of switching from a key to itself. You switch from your key to your own key, but in the process, you multiply the message by C. You can think of this as an encryption of C. And now homomorphic operations on ciphertext become the standard function addition and composition operation. From linear homomorphism, you can add up to ciphertext. If you have encryption of C and encryption of D, you add it to ciphertext, you get an encryption of C plus D. So you're multiplying by the sum. But now you can also multiply messages. Because if you compose two functions, if you first multiply by C and then you multiply by D, then the composition of the two functions is a multiplication by C times D. So the function composition, which is combining two switching keys, is exactly the same as ciphertext multiplication. And once you can do addition and multiplication, you can do everything. Now, so that's why, so some time third generation is considered GSW. Okay, so that's what characterizes the third or second, depending on how you count. Now, I think GSW deserves its own place. It's a point, it's a sort of isolated point. And what I think, what I like to call the second generation FHE schemes is, this was a result of a sequence of papers showing how this GSW scheme is particularly suited to perform bootstrapping. Now, bootstrapping is the operation of decrypting a ciphertext homomorphically. It's something similar to key switching, but it is, so I give you a ciphertext, I give you an encryption of the secret key, you decrypt homomorphically, you still have an encryption of your message, but in the process of doing that, somehow the ciphertext got cleaned. Lattice cryptography is noisy, there is some error accumulation, and if you keep computing, the error gets too big, and then you need, if you keep computing, then it's not a valid ciphertext anymore, so you need to do bootstrapping. And
basically multiply, when you're multiplying, it will
multiplying, yeah. So also when you add, you get the sum of the two errors, but sum is a very small increment of that. When you multiply, the error goes much faster, so that's critical. So, but there are two different schemes here. There is one which you use to encrypt the messages that you want to compute on, and then the one which is used to encrypt the secret key to allow bootstrapping. And originally, these were the same scheme. The way this was originally proposed by Gentry and then also followed by the first generation is that you want an encryption scheme which is somewhat homomorphic. It is limited homomorphic, but it is powerful enough to compute its own decryption function. So it was the same scheme that could homomorphically compute its own decryption function. Now, GSW, they didn't show how to do bootstrapping at all. They were just suggesting that you can do IBE, you can do all these other interesting applications, but for bootstrapping, they were just referring to the previous work, saying, yeah, we already know how to do bootstrapping. But after a few months, and this was again Brakersky and Vakuntanathan, I think January 2014, they showed how using the GSW scheme, you can bootstrap, you can homomorphically decrypt basic LWE ciphertext, learning with error ciphertext. So, and this is useful because the ciphertext is much simpler, but the scheme that you use to perform bootstrapping doesn't have to be optimized to perform arbitrary computations. You can try to optimize it to perform exactly the decryption operation. And this was further, there was a major development by Alperin, Sheriff, and Peikert the following summer. They showed that, instead of using branching programs, which is the model of computation used by Brakersky and Vakuntanathan, you can use arithmetic circuits, which are a much better match for lattice-based cryptography, also considering that most of it is just linear operations. And then this was further optimized in, that was my entry into, up to the point I was only reading crypto FHE papers. And I didn't want to write FHE papers at the time because they were so hard to read. I didn't want to write papers which are hard to read. And I mean, I'm not saying that my papers are easy to read, sure, my faults, but I try hard, yeah. And if I know to start with, there is no way to write easy to read simple paper. But I mean, this AP14 paper is the one where I felt like, okay, this is the right time to get in. And then I started working on it with Leo Ducas, which at the time was visiting me, as was a postdoc at UCSD. And so the first idea came from him, came from Leo, who said that I think that if instead of doing what Alperin, Sheriff, Peikert do, or these other these first generation schemes do, we use rings in this way, asymptotically maybe it's not the best scheme out there, but in practice it can be very efficient. So the complexity of lattice cryptography and FHE usually is a polynomial, but then usually there is a polynomial term n to the c, the n and square and cube, and then there is also a polylog term, log n to some power. And theoretically, we tended to disregard the polylog term because asymptotically is much smaller than n. But if you have many log factors, like log n to the 5, that's something that in practice can be way worse than n. So Leo's intuition was that, we can shave some of these log n terms just doing a quadratic computation using ring lattices, which ring lattices is my favorite area of lattice cryptography because it's something where I really feel that I have some major fundamental contribution. This paper of mine that you mentioned about compact knapsacks, it doesn't have the word lattice in the title, but it is actually a paper on lattices. We can go back to the name later if you want. And but then there was one other important contribution of this FHEW scheme, which is something that if I wanted, I could say that, that's what you should call generation. That's when you change from one generation to the next. So the one novelty, what I think is the main novelty of the FHEW crypto system, beside being more efficient, was that it introduced a different general model to do homomorphic encryption, which is the following. So when you do bootstrapping, just the same way as when you do key switching, you can multiply something by a constant. When you do bootstrapping using a scheme of the type of the DM type or the AP14 type, decryption involves a linear operation, which is easy, And then there is a rounding operation, which is done using a lookup table, basically, encrypted lookup. And once you're doing a lookup, if instead of doing rounding, you put something else in the lookup table, you can pretty much compute any function, not just rounding. So this allows to do something that you may call functional bootstrapping. I mean, we didn't come up with the name functional bootstrapping already back then. I forgot when the word functional bootstrapping was first used. Some people like to call it programmable bootstrapping, but that was the first example of functional bootstrapping. And the advantage is the following. Once during the bootstrapping, which is a unary operation, you take a single ciphertext and then you typically compute the identity function on it, just for the purpose of cleaning the error. If while you do that, instead of computing the function, you can compute some other function. For example, let's say if the message is a single bit, there is very little you can do. I mean, there are only those not, identity, and negation and constant functions. So let's say you have a bigger message space, 0, 1, -1, or perhaps numbers modulo 4, okay? And, or 0, 1, 2. Let's say 0, 1, 2. And you can compute a function that maps, say, 0 to 0, and, or maybe 0, 1 to 0, and 2 to 1. Okay, so it's a sort of rounding too. But this is an operation modulo 3 or modulo 4. So once you can do that during bootstrapping, in order to have an FHE scheme and perform arbitrary computations on encrypted data, it is enough to have a scheme which is linearly homomorphic. You don't need a scheme that supports multiplication. You don't need multiplication anymore. Because addition gives a way to do exclusive OR between bits. And if you want to compute the end between two bits, you can add them up and you will get 0, 1, and 2. But when you map 0 and 1, you map it to 0, and 2 is mapped to 1. That's basically doing the AND operation. You get 1 only when they are both equal to 1. Yeah. And this allows to do FHE using an encryption scheme, which is nothing else, nothing other than the most basic way to do non-homomorphic encryption using lattices. So that's the way that Regev suggested how to do public key encryption using lattices without even thinking about homomorphic operation, which in turn is just a lattice version of something that in the private key setting had already been suggested using codes over finite fields. So this gives you an encryption. So the way I think it is a reasonable place to draw a line between generations is because now the encryption scheme is just standard LWE encryption, something that existed even before Gentry. And then you have this so the scheme is naturally linearly homomorphic. And then you have this bootstrapping technique, this functional bootstrapping technique that allows to compute nonlinear gates, but they are unary. So you have a combination of gates with multiple inputs, which can only do addition, and the unary gates, which are lookup tables. So this is different from the arithmetic computation model used by the first generation of schemes. And where does GSW fall into this? GSW is not a method that is used to perform operations on your encrypted data. It is used internally to implement the bootstrapping procedure. This was one of the reasons. Sometimes you see our paper has been mentioned and described as an optimization of GSW, as a way to make GSW faster. It is not at all. It is true that that paper was the first time that GSW was not using ring lattices. So our paper was the one to propose a ring version of GSW. But since it was just a ring version of GSW, we didn't give a new name to it. People tend to give new names to every new idea, every new thing. We simply called it ring GSW. That's the name.
Yeah, DM. It's now known as DM or FHEW.
Yeah. So DM is based on the. We called it also. So why is the system called FHEW? So there was a pun on you know the FFTW library.
Yeah.
It's the fastest Fourier transform of the West, Matteo Frigo. So there was a very popular, it's still today, it's a highly optimized, very popular implementation of the FFT. And our paper was using ring lattices and the fast Fourier transform to implement things efficiently. In order, so we coded it up in like a little bit over a weekend, maybe 4 days.
Wow.
And we did it using the complex fast Fourier transform, using the FFTW library. Not because it's the best way to do lattice cryptography. You want to use the number theoretic transform for cryptography, but was the fastest way, was good enough, and we called it FHEW. Perhaps not a good name because that's not the way you want to implement it now. You want to use the number theoretic transform. But yeah, so we call it, that's why we called it FHEW. But what was new about the scheme was that's not the name of the ring GSW. That's ring GSW used internally. Then the outer scheme, that's what we called FHEW. And we debated a little bit with Leo about is this a good name or not? And Leo said that I don't think it's a good name. He suggested the name. And he had some doubts about it. And then I told him, no, that's fine. That's a fine name. Let's just use it. Perhaps we should have put more thinking into it. I think people don't quite know how to pronounce it. They
Few.
don't know it. Few. I mean, that's
Yeah.
what we meant. Few. But then,
Yeah.
and few. Anyway, doesn't matter. Those are just names. So there is. So another function which with I think there was a good name, but was not optimal that I worked on. So that's the Swift hash function,
Yeah.
which we worked on with. This was one of the very early papers in the implementation of lattice cryptography, 2008. Was with my at the time student Vadim Lubashensky and Chris Peikert and Alon Rosen. And we called it Swift with two F, Swift FFT. And the title of the paper was again a pun on Jonathan Swift. If you read the paper, it will be pretty clear. It was a
Yeah.
modest proposal about FFT hashing. But that's the paper that for the first time implemented very efficiently the number theoretic transform and showed that it is something that is not just theoretical, it's something you want to use in practice. It is so efficient, so practical that everybody started using it everywhere, often without even attribution. I think that when people use your idea and use what you did without even citing it, that's the best sign that, okay, so there was something fundamental. It is standard, doesn't even, yeah, shouldn't even be given a label or name. But then, much later, when talking with my co-authors, we came up with the idea, oh, perhaps we should have called it Sprint with two N, with two T, as in a number theoretic transform, NTT, to sort of suggest that, yeah, so that's where the entity was first used, and then
Yeah.
it became the standard way to implement lattice cryptography.
Yeah. That's excellent. Because
So I think I
I do,
exhausted the
yeah.
generations.
Yeah.
Yeah,
Yeah.
it's
Oh,
there is the approximate homo. You wanted to ask about approximate?
yeah. Yeah. Please.
Yeah, so that's something that I call 1.5. So even if
Yeah.
chronologically came later, it is something that is very technically is very similar to the first generation. It is basically Regev encryption scheme with a with a homomorphic operations, but without the error correction part. Take something which is a valid encryption scheme, and then you can make it more efficient by removing the error correction. There are many implications. So this is a fundamental change, including security implications. So that in some sense, once you do that, you have to be very careful about what you're doing. You may get something that is not secure at all. I had some work on that. It got a lot of attention. That was a little bit surprising to me because to me it was kind of obvious that until we wrote the paper, we didn't know how to formalize the fact that, okay, so there is some issue here. But the fact that error correction in the original scheme was serving more than just a functional purpose of getting correct results. It also had an impact on security. It was something that I already felt like that, yeah, this is something that we know, so we should think about it. But of course, it is a system that allows to do homomorphic encryption on approximate data much more efficiently. So it immediately, the efficiency attracted a lot of attention, and there's been some very interesting works done, mostly on the efficiency side, to push the frontiers of what can be done in practice using FHE, using approximate homomorphic encryption.
So the DM method is really quite excellent, and I think anyone can go and look in the OpenFHE library and implement Boolean circuits that really can build quite complex homomorphic circuits, where some of the integer methods and the floating point methods like CKKS are limited, obviously, to numbers. I think your DM few method really opens up homomorphic encryption to allow a whole host of applications. So, what do you think the main applications of fully homomorphic encryption might be, and what's the barriers? What's going to hold it back?
So efficiency, of course, is the main barrier today. Early on, it was not efficient; it was security. I mean, after Gentry's paper, some people were already concerned about efficiency, and of course, there's been a lot of progress on efficiency as well since the beginning. But the two things, improving security and efficiency, sort of went hand in hand. So there were simplification to the schemes, which at the same time were making the schemes more secure, easier to understand, and more efficient. At this point, aside from the theoretical question of whether we can do FHE without bootstrapping at all, I think the security questions are pretty well understood. But efficiency, of course, is the limiting factor. Already in the 15 years ago, people were talking about, oh, using FHE, you can do encrypted web searches. You can do encrypted, you can encrypt everything, and then everything we do on the web, we do in an encrypted form. I mean, the blow up in efficiency that you have to sustain to do that is so big that it is unthinkable of performing everything in encrypted form. We're getting, of course, closer, especially if you use hardware acceleration, but we are still pretty far. So in the end, I think that the best opportunities and barriers we have to look into what can be done with FHE. And that depends on the schemes. So we have these approximate FHE schemes that allow to do approximate computation. And this seems to be a very good fit for machine learning type of problems, where typically you have shallow computations. So computations, if you want to compute some statistics, I mean, computation is not a high depth circuit. And so that's something that can be done even without resorting to bootstrapping or resorting to bootstrapping sporadically. And that's why these are the applications that attracted most attention. And then there is the FHEW style encryption, which, I mean, the main library that specializes on that is the TFHE library. That's called the TFHE as FHE over the torus, because there was a follow-up paper to FHEW. They changed the name because they changed the underlying mathematical structure to use the torus, the 0-1 continuous interval, which for some reason I never understood. They thought it was the key to efficiency, which it turned out to be completely orthogonal. In fact, everything that you can do on that can be done on the original scheme as well. So you can think of it mostly as a different variant of the bootstrapping procedure, which has some advantages. And there's been work on both sides to make a few TFHE bootstrapping faster and faster. The OpenFHE libraries, I think they are trying to stay sort of name neutral, and these things perhaps are called FHEW/TFHE, or perhaps they started. I think VM is something that they started using for uniformity with first generation schemes, which were called BGW and BFW after the authors of papers. And there's been a lot of development for this bitwise model of computation that started with FHEW, with functional bootstrapping, where you compute gate by gate, but critically you have to perform a bootstrapping after every gate. So this gives something that is more general a nicer model of computation, just Boolean gates. They don't have to be Booleans. Already, shortly after a few months, already in our paper, we suggest that, oh, you can do bigger gates, you can do threshold gates, and there's been work.
Multiplex. Yeah.
Hmm?
Yeah, a
Yeah.
multiplex are good.
Multiplex, yeah.
Yeah.
The multiplex was one of the main innovations introduced first without using rings in this Jinx paper, which was not presented as the main contribution of the paper. The title, you have to find it, you have to read it and then find the section that has this multiplex operation. And then so TFHE adopted the ring version of the Jinx multiplexing. It was basically combining Jinx multiplexing with a few ring GSW operations. And there is a lot of work that can be done in trying to find the best way to build these gates, which is interesting. I think is interesting and important work that should be done. Sometimes theoreticians don't have enough appreciation for the engineering of optimizing these type of things. Even if personally I feel that that's the same as circuit complexity, one of the most theoretical areas of computer science. So it's not
Yeah.
something that we should consider as a lower class type of work compared to real theoretical work. And personally, I enjoy doing that type of work. On the other hand, while the first generation or 1.5 approximate FHE schemes, they have to use very big numbers. Once you use very big numbers, you have to use very high dimension for efficiency. Once you are using very high dimension, you can use this dimension to perform many operations at the same time. And then the cost of bootstrapping gets amortized. So few TFHE are schemes where the native bootstrapping operation was working on a single scalar ciphertext. And there was even a small one, like a bit or a few bit small word. And there's been work since then, including both work of mine and work by other people, on trying to find methods to amortize few bootstrapping. And I think it's one of the main barriers that we have, because right now we have methods which are asymptotically, they are fine, but they are not efficient in concrete terms. But if you find a way to do amortize few bootstrapping, which is both theoretically efficient and practical, so you can bootstrap many messages at the same time. So that's something that would give a very efficient FHE method with a simple programming model, rather than the first generation 1 or 1.5 generation schemes, which use a substantially more complex model of computation. That's something that could allow to make FHE much easier to use, usable. I mean, you could already do this now, but the efficiency, it would not be competitive in terms of efficiency. So people are focusing on more specialized applications. So I think that's what I would really like to see solved. A
Yeah.
practically efficient method to do amortized few bootstrapping. There's been some very interesting work in, I think, Eurocrypt 2023 with a very interesting novel idea, but unfortunately, it doesn't seem to be efficient in practice. The paper didn't implement it, so they leave it open as, oh, we don't know. But I mean, with an expert eye, I see the barriers. So there is some interesting work to be done that may require both the theoretical ideas and practical ideas.
And so what do you think the opportunities there is in threshold methods and multi-party computation within homomorphic encryption? And how do these methods work?
Okay, so it's not only opportunities. I think threshold lattice cryptography, and especially in the FHE setting, is something that opens both opportunities and dangers. Now, threshold cryptography, the opportunity is that you can take the secret key, which is a single point of failure. If your secret key leaks, then everybody can decrypt your messages. You can distribute it, and you can have many devices that have to collaborate in order to decrypt messages. And we know that secret key can get lost. So the possibility of distributing secret key material, of course, is very attractive. That's the basic of fiat of the Shamir secret sharing, and this is well understood. Now, lattices at first seem a very good opportunity to do that, because the simplest type of sharing is just linear sharing. Take many secret keys that add up to the correct value of the secret key. And decryption is linear, both in the ciphertext and also in the secret key. So you can use each of these key shares, use it as if it were a key on its own, decrypt using the key share, run the normal decryption procedure using the key share, and then add up these partial decryptions. So this is a very natural way to do that. But decryption in lattice cryptography is a linear operation multiplied by the secret key followed by a rounding. And as I already suggested when talking about approximate encryption, rounding is important not only for correctness, it's also important for security. So in the threshold setting, if you do this partial decryption and then you transmit them, and then you add them up, and then you do the rounding is done. So these messages are being transmitted and they are visible to the adversary before the rounding. And this allows to completely break threshold lattice-based decryption in a way that was already known in 2010. There's a paper, there was the first paper on threshold lattice cryptography by Bendin and Damgard, who were well aware of this problem, and they suggested how to address it by adding noise to these partial decryptions. Then you add them, and then you do the rounding. And there is a trade-off between adding noise that requires larger parameters, make encryption less efficient, and security. Interestingly, that's exactly how I forgot the year, 20 or 2021, with my student Bayu Lee, we came up with an attack to approximate homomorphic encryption, which was not doing the rounding, was saying that, oh, you don't need the rounding, so you can skip the rounding to make it more efficient. But if you don't do the rounding, you can essentially apply that type of attack and recover the secret key. Not only decrypt the message, you get a full, very efficient, practical and asymptotically theoretical key recovery attack. So at the technical level, there is a lot of similarities between securing approximate homomorphic encryption and securing threshold encryption. Currently, both methods rely on a form of noise flooding. You add some noise to your pre-rounded ciphertext to avoid the attack. And then you can also try to prove, you can prove that it is secure, but the naive proof uses an exponential amount of noise. So it requires very large parameters, even in the non-homomorphic setting. In the homomorphic setting, it is something that compounds with the cost of the large parameters required to implement FHE, and it makes it even less efficient. So theoretically, we know how to do things, but it is an interesting area that I think deserves some more attention and study, and especially ideas to make it practically relevant. So the opportunity is there, but we don't know how to do it in the best way. So for example, so I have a paper, recent paper with my student, former student now, Mark Schulz, where we showed that if you just want to do public key encryption without homomorphic operations, it is enough to add an amount of noise which is even smaller than the encryption noise. You don't need to flood the encryption noise. But that's something that uses the specific property of the ciphertext error distribution for a fresh ciphertext. So if you do homomorphic operations, then the error distribution has a different property. In fact, we don't have a good handle on what exactly the distribution is. We bound how big the error is, but the exact shape of the distribution depends on the homomorphic computation that you performed. And we don't know how to adapt this efficient version of threshold decryption to the homomorphic setting without paying the high price of noise flooding with much bigger noise.
Yeah. And I suppose we're at the point of trying to take our existing primitives that we have, like our Shamir shares and pairing-based cryptography, and we're trying to find them mapped into this lattice world. Some things we can, and some things have risks. Some things we're struggling with, like pairing-based cryptography. I don't think there is quite a match for that now. And you do so many other, you research into so many other methods. One of your areas is symbolic cryptography. Could you explain what that is and what the application is?
Oh, I'm happy you're asking about that. That's something that I mentioned very early on. Cryptography, like pretty much everything in science, you can try to analyze at different levels of abstractions. And you may say that every system, every complex system should be analyzed at a level which is as abstract as possible, but not more abstract. If it is more abstract than that, then you lose in precision, you don't get accurate results. On the other hand, you want to abstract from details, low-level details, which are not really relevant, just to keep your problem simple. Now, cryptography, I think it's fair to say that the edifice of cryptography grew so much during the last 40 years that it's really about to fall down. I already felt like this 20 years ago, that the cryptography has already reached a sort of critical point where in order to do more and more and more, which is what most people seem to be interested in doing, you end up designing systems or writing papers which are incredibly hard to read. Part of the hardness is because the paper has a new idea. Okay, so part of it may be unavoidable. But part of it is also because we don't spend enough time thinking about what is the best way to describe cryptographic protocols, what is the best way to describe the security analysis of those protocols, and we just do everything the way we are used to as cryptographers. But revisiting the way we describe things is something that I think could be, I think is the only way forward. We can still maybe do a little bit more the traditional way, but we need to look into this. And a symbolic cryptography is something that falls a little bit into this area. So instead of, so in cryptography, you want to consider arbitrary adversaries that can look at the bits that you're sending. They can do anything they want. Maybe today's you should even consider quantum adversaries, not even classical ones. But yeah, so they have concrete access to your data. But that makes it very hard to describe and analyze the protocols. Now, in symbolic cryptography, you try to abstract from these low-level details. You want to think of cryptographic operations as an abstract data structure, where you can do encryption, which is a sort of constructor, and then you can decrypt, and if you have the correct key, you recover the original message. That's the only thing that you can do. There is nothing else you can do. Now, that's perfectly fine in normal software engineering. You're writing a program, you can decide what language to use to implement your program. You can use a high-level language to get strong guarantees in terms of correctness. Great, fine. There is something that makes cryptography different, very different from most software activity, which is you cannot force this on the adversary. You cannot tell the adversary, "Hey, since I implemented my my cryptographic primitive, I don't know, in say Rust, just to name a recently a popular programming language, which is touted as being safer than similar C-like alternatives. Also, the adversary should write the attack in Rust. I mean, this is just out of the game. Okay, the adversary can do whatever they want. So the idea of symbolic cryptography, or more specifically, what is called computationally sound symbolic cryptography, is the following. So you have two different levels of abstractions. So think of this as programming languages. So there's a kind of analogy. You have a high-level programming language, which is that of symbolic cryptography, where you don't get into the details of how the data structure works. You just treat it abstractly as these are the operations you can perform and nothing else. And then there is the implementation level where you have an actual computer. Theoreticians like to call it a Turing machine. Nobody really uses Turing machines in practice, but yeah. So to some extent, the computers that we use are pretty close to a Turing machine. So you compile your abstract cryptographic protocol into a concrete implementation. So doing this makes sense. Typically, this is done using software libraries that map the calls to cryptographic operations to their implementation. And then if the library is correct, then if you encrypt and then decrypt, you get the correct result as expected. Now, getting the correct result is a pretty low bar when it comes to cryptography. The essence of cryptography is security, is not correctness. So you would like also to have some kind of reverse compiler that takes any possible attack to the implementation of the cryptographic primitive written in the low-level programming language, using anything the adversary may want to use, and sort of reverse compiles it into a sort of ideal attack to the symbolic cryptography. And then, so you have these two compilers going in different directions. One that is applied to the implementation, the other one which is applied on the attack. And then you want to show that for any abstract cryptographic protocol and for any concrete adversarial attack, if you compile these two in the two opposite directions, whatever is achieved by the concrete adversary on the implementation is achieved similarly by the symbolic adversary on the symbolic protocol, which means that if you analyze your protocol in the symbolic setting and you show that there is no symbolic attack, then you can conclude that there is no attack also in the implementation, because you can map it there. And that gives you the best of both worlds. You get a simple description and analysis of the cryptographic protocols, but something that still gives strong cryptographic guarantees. Symbolic analysis without strong cryptographic guarantees had already been considered a long time ago. This was popular already in the 80s, in the 90s, and it was very effective in finding attacks. But it never provided strong security guarantees, because it was somehow assuming that the adversary is also using the symbolic method, the symbolic level of abstraction. And so I worked a little bit into this computationally sound symbolic analysis. I'm still active a little bit on it. And is not what most cryptographers nowadays are interested in or even understand. You need a little bit of a programming language or logic type of background to work on those things, which is very different from the complexity algorithms background more common in cryptography, but I think is something that is both technically interesting, but also a very good opportunity to move forward with more robust methods to build cryptographic systems and secure systems.
Yeah, I agree, because you've got Python. Python isn't really actually very good at implementing mathematical methods and proofs. You've got Sage, which is a bit better, and you can actually start to abstract things, but Sage is about as far as we've actually taken it without it becoming almost like mathematics, which is taking it too far. So we've never found that balance. So
There is this
in
trend, so I don't know if you heard about this lean
no, yeah,
theorem
yeah,
prover or proof assistant. This is
yeah.
something that's getting a lot of traction in mathematics.
Hmm.
I think it's something that could be useful
Could be
in this
used, yeah,
setting. And
yeah. Yeah, I think that would be very useful. So we've got things like Reed-Solomon codes, which protected CD-ROMs and made them work. I remember when CD-ROMs first came out, they used to put jam on them and put them into the CD, which wasn't actually true. It was all set up. And you've got things like Hamming codes and so on. And people like Maclise started to look at the opportunities of creating error codes within cryptography. It kind of lost its way for a while when RSA came out and elliptic curves and so on, but error correcting code seems to be back on the agenda. So can you just outline how you can use error correcting codes with cryptographic methods?
Yeah, I mean, for me, they never left. They were always there, error
They're
correcting
there?
codes, and there are
Yeah.
strong ties between lattices and error correcting codes. Now,
Mm.
make a list type of systems. These are used the digital error correcting codes where you have Hamming errors. So
Mhm.
every symbol gets flipped or not, and you look at how many flips you have. But there are also these things called the lattice codes or codes in Euclidean space
Yeah.
where code words, instead of being sequences from a finite alphabet, they are pointing Euclidean space, so lattice points. If you have a linear error correcting code in Euclidean space, is exactly a lattice.
Yeah.
And this is used implicitly in the way we do lattice cryptography, except that typically we use really the simplest error correcting code, which is just a scalar code. And we do round. When you round, when you have, say, non-integer point in space, and you round every coordinate to an integer, essentially you're using that as an error correcting code. If you encode if you have a finite alphabet, you can encode it as multiples of 1/2, and then you check whether you are closer to 1/2 or to 1. Okay. Now, you could try to optimize lattice cryptography using general error correcting codes, and you can also try to use error correcting codes for quantization to compress a ciphertext and making lattice ciphertext smaller. This is something that I explored in a recent paper on error correction and quantization in lattice cryptography, which somehow described as a general framework that combines the two things. But so you were interested, I think your question was more along the lines of shall we use the traditional finite field type of error correcting lattice-based cryptography? So what's the of course, it never. That's also something that was always there, and there's been research on it. We still have research on it. It was still considered for standardization, and during the recent NIST post-quantum standard. And now, personally, I don't.
HQC, I think HQC has been
Yeah,
standardized, and
yeah,
I think that's an
yeah,
error
that has been
correcting code.
standardized. Yeah. Now, personally, I never drew a big line between code-based cryptography and lattice-based cryptography. They have so much in common. It is just the same thing using a different mathematical structure. Then we can look at the merits of one or the other method. And there are different aspects. One is the efficiency. Okay, so or how big are ciphertexts? How small are ciphertexts? Often, especially in a context of standardization, people look into these problems in concrete terms for the level of security that we want to achieve. And based on the best currently known attacks, how many bits is your ciphertext? Now, this is certainly very important in practice. It's not a question that personally I find particularly interesting to explore myself, because it is something that can very easily change well, not from one day to the next. Perhaps, I mean, if you pick the right day, yes, from one day to the next when a new attack is discovered. But we should look, I'm more interested in the asymptotics. What can we say about the fundamentals of these methods? And I think that the fact that for lattices we have this connection between worst case and average case connection, I still consider it to be a really big selling point for lattices. Even if the connection is not tight enough to be relevant to set key sizes, it still provides a conceptual guarantee that you're on the right track, that you're using the correct distribution of lattices. And we don't know how to say that for codes. So you may use Gopa codes, you can use some other family of codes, and there are very variants of make-a-list have been proposed. And we don't really have a way theoretically to discuss which of these methods is the best one, which one should be used. We are all working based on the currently best known attack, which is a perfectly fine thing to do. I mean, don't misinterpret this as saying that this is something that should not be done or is not interesting or not important. But I think it's fairly limited to what we were able to do with lattices. And try to do something similar for codes, even if it's not practically efficient, is something that I think would be very useful to increase our confidence in those schemes and also attract more attention, more people working, moving from lattice crypto to coding-based crypto. But I guess it would be the same people working on a wider range of problems.
Yeah. And I suppose in the NIST competition, the lattice methods won. So Kyber, MLChem won in key exchange because it was the fastest. It had fairly good key sizes and also ciphertext sizes, where the code-based sometimes created very large keys and were very slow. Even the hash-based methods like Sphinx Plus is still pretty slow, but it's rock solid in terms of security. So I think NIST know that the lattice ones are probably the best for performance and general use, but they want to have a backup of the error correcting codes, which seem to be a bit more secure, possibly. They've been around for a longer time, for one, and obviously the hash-based methods, you can't go wrong with a hash-based method overall. So you could have patented the DM FHEW method, and probably you would have done very well out of it. And there are some methods in cryptography, such as RSA, that was patented and went on to be very successful. MIT decided to aggressively patent it or protect it. It became a company. You see things like Peter Shor's methods not being used for signatures that have become ED-DSA. So, what's your viewpoint on patenting cryptography? Is it a good thing or not?
Um, Depend at what level. So I think that for a few, we didn't even consider patenting it. In fact, we even got some negative feedback from people at companies complaining that the code that we implemented in 4 days, we released under the GPL, the GNU public license, which makes it hard for companies to use. I mean, we picked that one because implementing things is not something, it's not something that we do on a day-to-day basis, and that's the little license we knew about. But I think that for cryptography to be successful, it is important to have a wide community of people contributing to it, and patents can be a barrier for that. And or in the FHE area, also the foundation, it has so much in common. These schemes have so many similarities and building blocks used in different places that I think it would be a pretty hard call to say that, oh, this scheme is covered by this patent, and all these techniques which are used by the scheme and were already suggested in the previous schemes, they were not patented, and so they can be used freely. So we borrow and lend freely in the standard scientific publication environment, and we give credit. So giving credit is important. I think giving credit is more important than patents. So patents often are described as something which is important and useful for something to be used in practice.
Okay, so this is my penultimate question. And it's a very difficult question. And if you had a crystal ball, what would the next decade look like in cryptography?
Hmm. Maybe this is a better question for Chris Peikert, who did an excellent job at yeah, describing some previous decade. So lattice cryptography, it's hard to tell, I think, moving forward, meaning that we have done so much, and sure, there are a few more things which are still work in progress, including currently the proof systems, snarks, lattice-based succinct proofs are a very interesting active research area. Interestingly, it is something that is based on the SIS problem, something that could have been done already in the late 90s, shortly after ITI's discovery. It's not using the learning with error problems, it's using SIS for the most part. And so that's a very interesting area overall. And lattices, they seem to offer some good opportunity to do it. But it's more of a technical problem to work on and make progress on. So any major thing that could happen in lattice cryptography, uh, what else is left to do? Well, obfuscation is one of the problems that you still may consider to be half open. I mean, they started using lattice techniques but in a non-standard way. It was being broken. We couldn't really do it. I never worked on it specifically, but a lot of good people tried very hard, and we people came up with something and now is considered as obfuscation from standard assumptions, but they are not lattice assumptions, and it is like three or four different assumptions used at the same time. Finding the right way to use lattices to do it using just a single but powerful, strong lattice assumption is something that could have also many other unintended consequences. And in the process of doing it, which is a big technical challenge, we may also come up with some other discovery. So perhaps this will happen in the next 10 years. So other than that, I would step out of just the narrow area of lattice cryptography, consider cryptography more generally, and I really think that this may be the decade where the formal verification somehow gets traction in cryptography. There are a lot of things pointing in that direction, both in and outside of cryptography. Perhaps lattices with all the mathematics of lattices may not be the best area to do that first. Some other simpler type of cryptography is what will be sorted out. There is already quite a lot of work being done, but it is certainly not mainstream yet. I really envision a future where people will write papers with formal proofs of cryptographic protocols that can be checked by a machine. And not just because nobody wants to read the proof. In the process of finding a way to formalize the proof that way, they will be forced to come up with simpler proofs as well, or proofs which are described at the right level of abstraction.
Yeah.
But
And
yeah.
we need to compose down into the key elements and then make sure each element is secure, and then that builds into a higher level security. I think you're completely correct. So for my last question, I've got two parts of this. So you've obviously learned a lot in your academic career about research and how it's developed your career as a professor. Is there one bit of advice that you would give yourself as a early career researcher or any early career researcher as to how they can best optimize their career? And also, is there one thing in your career that you would have changed that would have enhanced it?
By and large, I'm happy about what I did, but I often felt dissatisfied or even disappointed about the ordering on when I did things. So if there is something that I would change, perhaps, is the timeline. I often felt that many of the things that I did, I did it at the wrong time. So whether something gets traction or not depends not just on the quality of the work. It depends on the community that is out there that wants to see that and is ready to use it. So I worked on lattice cryptography. I started working in lattice cryptography when it was not popular at all. For people that started looking into lattice cryptography, more recently, it may be unthinkable. Oh yeah, there was a time when lattice cryptography was not popular. Oh yeah. It was incredibly unpopular. The mainstream opinion was that lattices should be used only for cryptanalysis, not to build cryptographic functions. But on the other hand, if I had not done that work back then, much of my work was in trying to build a simple, easy to use, and still solid foundation to do lattice cryptography. Both to convince people that it's efficient, then you can do it in practice, and also that you can do it in a reasonable way where it's not too technically difficult to work on it. Perhaps if I have not done it and said, oh, let's do it later when somebody else does it, who knows? Perhaps nobody would have, not nobody, somebody would have done it sooner or later, but who knows when they would have done it. Perhaps it would have been too late in my career to go back to it. So overall, yeah, I really don't know what I would change. So I'm happy about what I did, and I'm pretty satisfied with it.
And the advice that you would give your earlier self or an early career researcher as to how to improve the research?
Ooh. Probably talk more to people I mean, the crypto environment is quite collaborative. People talk to each other and so on. But I think there's a tendency sometime in to isolate because it's the only way to make technical progress on a very difficult problem. And I probably erred on the side of working too much on my own than with other people than what would have been optimal. Not that I mean, I'm happy about collaborating and sharing ideas, and but overall, I probably would have done more if I had allocated more time to just collaborations and exchanging ideas with others.
That's good advice. And obviously, going to conferences and going to a range of conferences and listen to other people's ideas is a great thing to do. And I think COVID didn't help that kind of approach, but hopefully things are going back to normal again. So thank you so much. It's been so interesting, and I think your work has really been amazing, especially with the DM Few Swift method. I now know that it has another name now, and I highly recommend anyone to go and actually have a look at some of the implementations, such as with OpenFHE is a great library to implement a range of methods, including DM, CKKS, BGV, and so on, and really experiment and really see if we can get these things to work and build new types of systems. And I think once the ASICs and GPUs become standard and consume less energy, then we could actually see fully homomorphic encryption changing our world. The holy grail, as you would define it, of cryptography. So thanks very
So,
much,
so
and
as
hopefully
sorry,
we'll catch up soon.
sorry, as you mentioned libraries, I'd like to add, if it's okay.
Yeah,
So as you mentioned libraries, I'd like to mention beside OpenFHE, this other
mm,
library written by Chris Peikert called
yeah,
LOL by
yeah.
Chris and Eric Crockett. Is a Haskell-based library, so it's not the
Haskell.
programming language
Wow.
that most people
Yeah,
use. But I
right.
think it's a very, very interesting project, and people are not looking at it because it's not the programming language that people are used to. But I think that there is a lot of interesting work that could be done in the intersection between cryptography, FHE, and type system and programming languages to get a nice framework to do some of these things.
Yeah, that's good. Can I ask you one last question?
Yeah.
I'm into Rust, Golang, C Sharp, Java passed me by, C++ passed me by a bit. I program in C too. So you did mention your love of programming languages. So could you just give us an example of what languages you enjoy using?
So I really like Haskell, which is a functional
Mhm.
programming language. It's not the language. It's not that I. There was not a language used for training. It was not my first language. Of course, I started with basic imperative programming and so on. I sort of rediscovered Haskell. I had some brief exposure to a precursor of Haskell when I was in undergraduate in Italy. The
Mhm.
language was Miranda at the time, but then I forgot about it. I rediscovered it in the early or mid 2000. The language has a very nice, beautiful mathematical structure. It is simple in the sense that there is a very small core of
Mhm.
well organized structured operations that you can use. And so you don't need to learn and remember a lot. You just learn the core and then you use those things over and over, which for people like me that don't write programs on a daily basis can make a big difference. It's convenient. And many times I tried to use Haskell for lattice cryptography. Every time I ended up being disappointed in terms of performance, which is also perhaps also one of the reasons this LOL library is not being used. Maybe it's not just the language. Even if the library has a C++ backend, but still the performance is not competitive with other libraries. But I think that the programming language is not just a way to write programs that you can run and get the result. A language is also a way to describe ideas. So having a language that allows to abstract things and describe things at the right level of abstraction is something that can make programming both more pleasant, more robust, and it can also be a source of new ideas. So once you have the right abstractions and you're not cluttered with all these details, maybe you will see some opportunity that was not clear before. And so Haskell is a language that from that point of view is way above many of the other languages that you mentioned. Some of these languages, like Rust, they borrow many ideas from Haskell. And it is still considered, I think, more of a research programming language. It is used in industry to some extent, but is I'd like to use it more for research, but when it comes to implementing an FHE library, I couldn't quite find a good way to do it yet. But Chris and Eric library is a very good project that perhaps if more people looked into it, there could be enough progress to get something interesting out of it.
Great. Yeah. Yeah. Looks like C is the common denominator. Python also generic. I see quite a lot in Golang just now, and obviously Rust is taking over greatly in terms of memory safe code. Obviously, we didn't talk about side channels at all, which are a big problem in cryptography. But that was my last question. So thanks very much. I've taken a long time out of your day, but I hope you have a great rest of your day, and thank you so much. Thank you.
Okay, thank you for having me. Goodbye.